Hello everyone. We are from Shrimp Allergic Group, and our product name is NSET, Deep Brain Stimulation Device.
Okay, so we're going to present to you about DBS, which stands for deep brain stimulation. It is one of the means of neuromodulation used to treat neural disorders such as Parkinson's disease and epilepsy. But the word neuromodulation, it simply means ways to alterate or manipulate neural activity in order for elicitation of a desired neural response. So neuromodulation can come in many forms, such as magnetic stimulation, ultrasound stimulation. In this particular project, we're trying to design multi-disease compatible DBS specifically for diseases such as Parkinson's disease, epilepsy, and depression.
From the block diagram, it has four parts: IPG or implantable pulse generator, electrode, external device, and target. Each arrow color has a different meaning as indicated in the figure. About the design, it has separated into four parts, six pieces, such as top and bottom case, cover all over the components inside. Top and bottom nest support the circuitry part, wheel band secure the top and bottom nest, and head protect the part that is a connection with the outside part. These are the components and the materials that each of it is made up. We separate into four parts: lead, extension, stimulator, and borehole cover. These are the materials along with its property.
Our lead design is based on the design of Medtronic 3387 model consisted of three main parts: electrode, marker, and connector. The electrodes are located on the proximal end targeting the target, with radial strip markers used to locate lead orientation nearby. These cell end connectors connect lead and extension, which will connected with lead plug and neural stimulator respectively. The lead has three layers: jacket, filler, and lumen. Jacket have pores and doped with dopants will act as distributed shunt between the filler and patient's body. The filler layers have high impedance and made them function as heat choke and made our lead MRI compatible. The last layer, lumen. There are two types of lumen: the central lumen for stylet and delivery service of lead, and electrode wiring lumen for each electrode contact wiring. The extension design was quite similar to lead, but without the electrode level. Apart from that, there are three main differences. The first difference is the diameter, which was doubled from the lead. Second, the filler coiling, which was helically coiled within each lumen, but the lead coiling was correlatively with other members. Last, extension tend to be stiffer for easier insertion. The electrode was designed in 1331 contacts configuration, one contact for ring electrodes and three contacts for segmented electrodes. There are three segments for each segmented electrode and made them support bidirectional stimulation and current steering. Anode shielding was the theory behind them. The stimulation segment will be cathode, while the other two segments will act as anode shield, preventing stimulation field from going beyond. This was the CAD design of our cylindrical lead with 1.2 mm diameters and 40 cm height. The four electrode levels and spacing between the lead was 1.5 millimeters. Alpha and HFO band or high frequency oscillation bands were part of LFP or local field potential. The reason we chose these two bands is that alpha band was the biomarkers of Parkinson's disease and depression, while the HFO was biomarker for epilepsy. There are three recording phases: intraoperative or surgery via implanted electrode connected with neurophysiology monitoring device; perioperative period via the cable connected to external digital amplifier; and last, long-term perceptive via the lead and neurostimulator implant. The OFP can be obtained from the difference between positive and negative recording electrode. There are two sensing configuration A and B under the same condition that sensing and stimulation electrode level should not be the same. The two configurations provide different LFP level access to target, locating at different level. Burr hole was used to cover surgery wound and secure locked the lead in place to prevent lead migration. The burr hole cover we choose is Medtronic Sensite burr hole. The model consisted of three main components: ring, cap, and screw. The base and cap was locked together after lid was locked in place with titanium screws. There are two reasons that we choose this model. The first reason is the ring of this model was flexible to place in any orientation and fit naturally on screw. The second reason is the cap that is transparent, which provides visuality of the lid underneath.
Okay, so the new part will be circuit detail when our system use electrocorticography and local field potentials will be an input. The output, as we expect, is stimulation impulse. We're starting by the contacting electrode going to amplification, filtering, and classifying until we got the stimulation parameters. Note that we use two channels for data acquisition to cover the biomarkers for Parkinson, depression, and epilepsy. So the first stage, neural sensor stage, where we use the AD8232 for recordings. It has a potential for common mode rejections of 50 to 60 Hz. It can implement low and high pass filters, and including it has a fast restore circuit to decrease the settling time of the signal. As the play here in the pictures, it is a light leg drive amplifier where capacitor acts as an integrator and resistor to limit the current to be less than 10 microampere. And point B is the passive first order high pass filter, and point C is the active second order low pass filter. And point D is a fast restore circuit in which we don't need it in high frequency channel, so we connect it to the ground. And we can use the PD6 pin from the microcontroller to control the activation status of the AD8232s. So the second stage is program amplification, which is simply a non-inverting amplifier where a reference voltage of 1.25 volt is supplied, the same as the neural sensor. We use TSC1224 and operational amplifiers. It has high accuracy and is widely used in biomedical signal application. Also, we use MAX5479, which is a digital potentiometer, as a variable resistor, where the value will be controlled by the microcontroller to I2C protocol, and there will be a pull-up resistor to prevent the signal loss.
In the part of digital control system, we employ the ATX Mega 32E5 as a microcontroller, which has the ability to optimize the power consumption compared to its speed, which is million instructions per second. It has the ability to convert the analog to digital input together with digital to analog output function, as seen in the picture. This microcontroller provides a variety function inside the pin, so it can be used in many different applications. Another important part in the DBS is the supportive reference voltage, which will help to generate a stable voltage to the circuit. In this case, it is 1.25 volt for neural sensor and 2.5 volt for neural stimulators. For the third and fourth stages are signal processing and stimulation. The output in the previous stage will be sent to the microcontroller, whereafter it is completely proceeded. The microcontroller will provide a stimulation parameter including the amplitude, duration, and frequency. As can be seen in the picture, point A is a digital potentiometer, which acts as a variable resistor where it controls the amplitude of the stimulation pulse depending on the severities of the disorder. Next is point B, an N-channel MOSFET for switching on and off to create a pulse-like waveform. This action will produce the stimulation frequency and pulse width. For point C, it is an adjustable current source that takes voltage supplied as an input. Lastly, point D is an inclined blocking capacitor for transforming a monophasic waveform from the power supplied into biphasic form for passive charge balance compensation to ensure the neural polarities of the tissue. Let's move on to the monitoring unit. We selected the RN4020 as a Bluetooth module because it has a low power consumption together with the ability to operate ISM band or Industrial Scientific and Medical Radio band in the range of around 2.4. It also allows the multiple input and output channel to control the status and hold the information from the microcontroller. Therefore, it can be used to monitor the frequency response, procedure signal, and the battery status from the DBS. Next is the power supply stabilizer, created by using a 100 nanofarad ceramic capacitor and 470 microfarad tantalum polarized capacitor. The role of these two are a bit different, however both of them do support the power supply to be stable.
Next is algorithm and classification. The microcontroller will receive and extracted biomarkers which are alpha wave and high frequency oscillations. Then begin digitalization until the result is smooth signal is obtained. For disease classification, there will be a threshold for both biomarkers, which we use to subtract it with a smooth signal, and we use this error to determine the disease using fuzzy logic classifications. From the flowchart, the condition 1 means that there is no significant sign regarding the specific biomarkers. For example, a Parkinson's disease that is identified by using alpha wave and high frequency oscillation. If the result showing a significant errors when comparing to the threshold, then the symptom is considered as a Parkinson's disease. For severities, there will be two thresholds for high and low severities, so we could determine how the condition of the symptom is.
This is our internal circuit block diagram. It will start from sensing the signal in the brain, then send the neural signal into the circuit. And finally, the stimulated impulse will be sent back to the brain by the electrode.
About the battery, we choose the primary battery as lithium-ion, which is Conteco 440 mAh from Eagle Picture Company. The consideration of batteries such as lightweight, longevity, sustainability, safety, and others. These are some of the specifications shown in the slide. How to know the battery life of the device can be calculated by this formula. For the load current, we have three modes with two current paths. The battery life depends on the disease and symptoms of a patient. Each disease and patient has a different frequency of symptoms. The more it happens, more often the stimulation will occur, then the battery will decrease faster. In Parkinson's disease, battery life is around 6.5 years. In depression, it's around 2 years. About the future improvement. From the type of battery of the neurostimulator, we can improve it to be a rechargeable battery. The rechargeable battery is a secondary battery. It makes the life cycle of the device longer, so an external component will consist of a power supply, recharger, and antenna. Power supply before the electricity enters the recharger. It will be transferred from alternating current to direct current. Recharger, it has the function of storing the electricity and functions as a controller of the stimulator. The antenna has a function to communicate with the internal component by resonant inductive coupling method, which is wireless power transfer and consists of two parts. First, resonant coil on the transceiver side in the part of the antenna circuit, and second is the resonant coil in the receiver side in the internal component. The benefit of using the rechargeable battery is that it is more suitable for diseases and some patients whose symptoms occur very often, like epilepsy.
So we mentioned earlier that our design used a passive charge balancing compensation as an insurance for safety. However, for future improvement, an active technique could be applied as this is the best way to ensure there will be no residual remaining. We may use the current sensing amplifier to sense the charge injected to send out the inverse injection to match a pulse perfectly. By switching the anodic and cathodic phase based on the MOSFET configuration of the right picture respectively, it might be placed at the position B as suggested by the 80418 datasheet for H-bridge circuit, and it is a direct measurement. Why if we place at point A, it will be able to detect the short-lived load, while the point C has low cost and low common mode voltage. The reason we designed to put an active charge balance in the future improvement is that we are not certain that actual design will be more complicated than what we have shown or not.
Okay, so in terms of navigation system, there are generally two conventional methods of implanting the DBS system. The first one is using stereotactic frame, and the second one is frameless with fiducials attached on skull. On the left here, you can see an example of use of stereotactic frame, and on the right here, you can see an example of the use of fiducials attached within the skull. So the technique that we've chosen for implanting the DBS system is frameless and fiducialless implantation technique, which is developed by Dr. Holloway in 2020. These are the requirements for this particular technique. First, we will need an MRI scan, CT scan, Medtronic's or arm imaging system, Medtronic's cell station, Medtronic next frame, and Medtronic stim lock. Okay, so this is the summary of the overall surgical operation. A few days before the actual surgical operation, the patient will be appointed for taking two sets of MRI, which are volumetric T1 and T2 turbo spin, and another CT scan of the patient's overall head. During the surgical operation, the O-arm scan will scan the patient's brain again, and the image will be combined with the previously mentioned MRI and CT scan in order to calculate trajectory and the entry point of the electrode by using this Medtronic cell station system. Once the entry point is determined, the patient's skull will be incised and drilled at the calculated entry point. Then, the attachments of Medtronic stim lock and next frame will be made, along with the use of O-arm scan again. Before implanting the electrodes, we will need two tests, which are microelectrode recording and microstimulation tests. Microelectrode recording is essential for determining the borders of the STN. So in this particular technique, in this research, they're doing it on the patients with Parkinson's disease, where their target tissue is the STN, which is the subthalamic nucleus. And macrostimulation test is essential because we'll need to determine the threshold for any adverse side effect during the stimulation. After the tests were executed, then the electrode implantation will be executed. After the operation, an O-arm scan will be made and the image will be fused again, combined again, to confirm the position of the implanted electrode and in the stealth station system, and the patient's scalp will finally be closed. For this particular technique, the results, if compared with frameless and fiducials, there were no significant difference as shown in the figure on the right below here. You can see that I've separated 4 columns of information. These are the errors determined from, the first column is determined from errors from between 2 points from the actual electrode implantation and the planned trajectory implantation. And you can see that the errors aren't that significantly different. So the first column will be the errors calculated from 3D space. The second one will be errors calculated from the x-axis, then from the z-axis and the y-axis. And the researchers suggest that using a stereotactic frame will reduce accuracy due to weight bearing on the frame produced by torque. And in this technique, they also suggest that the use of O-arm has yielded good accuracy, and that the procedure is best tolerated by patients and operation time is shorter. However, the downside of this technique is that patients have to be frequently exposed with radiation from the O-arm scan, and it will require a long learning curve to achieve accuracy.
Regarding the safety standard, we use standard system, both ISO and IEC for our device. We spread into many types such as quality, system, electrical, sterilization, biocompatibility, software, test, and welding.
Okay, so that's all for our presentation. Thank you for your kind attention, and here's our members and roles.